Okay. How's everyone doing?
Oh, good.
Good. This is the face of someone who's exhausted. It was like a third day of the weekend. I would write an email about that too, but spring forward is a funny one.
Yeah.
Because you're like, oh great, I get to sleep in. It's like, wait, no. Don't get to sleep in.
Oh,
Last. So the sun goes down later, great, except for you're not tired till later. Bad. And you have to wake up earlier. So I'm exhausted, didn't sleep well, and I'm worried that I'm underprepared for today. So if today's lecture goes short, that is completely on me, and I'll apologize ahead of time. But we're gonna make a transition, told you that the transition was coming. And unfortunately, probably the first couple classes, they're gonna be very mathematically technical and not very interesting. So I'm gonna try and keep them engaged in the physics, but if you fall asleep, I totally get it, I wanna do the same thing. Is that reasonable?
All good.
All good. Okay, so you're either reading in this. Maybe you went out on a limb and you got one of these, right? And so now we're gonna look at the tensor section. Because I'm gonna assume that you guys are fully competent in vector mathematics. Right? Dot products, cross products, no problem. Okay, matrices, how do you feel about those?
Okay.
Yeah, más o menos, okay. Scalars.
Yeah.
I know numbers. You dumb? Okay, so 2, yeah, I know lots of scalars. Okay, so before we get started today, we're gonna talk just sort of like what the impetus of studying tensors are and what all these terms mean, because I'm a big fan of definitions and in particular in using definitions properly. Okay, so what's a scalar?
Isn't it just the magnitude?
Yeah, no direction.
It's
Scalar.
like a measurement with like the direction associated with it.
Oops. Okay, see, I already just 7 letters in and I already don't know how to spell. Magnitude. No direction. Okay, what's an example of that?
2.
2, okay. Mass,
That's, oh,
That's not velocity.
interesting, speed, good choice there. Okay,
right.
anything else? Volume is a good one. I think of like 5 more, so I want to see how many we can get on the board, just 'cause we're gonna wake our brains up.
Charge.
Charge, very good. And similarly,
What, like resistance?
no. Of course, we could do all of the divisions by these, but I want to think about it in the context of like sort of the base unit types.
Okay, base unit.
If you think about charge, you think about quantum mechanics, you're also thinking about spin, spin.
Up and down,
Oh, interesting.
but it's those just magnitude.
Well, the question is what about the magnitude of the spin? That would be a vector, that would be a scalar, right?
Yeah.
I haven't
So
seen
just
one.
one half or one.
Oh, you haven't taken quantum, okay, no, let's continue, I won't even say that I said that. That's good, keep going. Anything else? My favorite one for today, because I've experienced a lot of it.
For me.
I was gonna go with temperature,
Huh?
so,
How much temperatures you experience?
I know, yeah, but if you came in today, right, it was like really cold coming out of your car. And then you get back in your office, you like turn the heater on, you're nice and warm, and then you walk in the halls and it's freezing, and then you get in this room and it's hot again. That's a personal experience that you didn't know that I had, but that's what I'm telling you about today.
Okay.
Anything else?
Yeah.
What? What's the most important one?
Money.
Oh, true though. That's all constantly going down, okay? Time, there we go. Okay. All right, that's good. You said you already gonna spend 20 minutes, that's correct. Okay, so that's the definition of a scalar, sort of to our understanding physics. So what's the difference between a scalar and a vector?
Vector has the direction.
Vector, magnitude, and direction. Okay, that's kind of the feel. Examples of that.
Velocity.
Good.
Forces.
Forces.
Acceleration.
Right, that's sort of part of this, but
Yeah.
yeah,
Lots of things.
lots of things.
I was gonna say current.
Let's see if we can connect any of these to these. So you got speed from velocity, great. You have charge, what is, okay, good, so you could have like field direction. Let's say B or E fields. Is that fair? Okay, and similarly, you can see some connections here between something like acceleration and mass and forces. Okay, anything else? They don't have to pop to mind, that's okay. I might also go up here with something like energy. Another basic one for vectors. Positions vector, right? And so then things like angular momentum, of course, are vectors, right? Okay. Okay, so now we get to the third step here, and this is the one where we get a little bit more abstract. What is a matrix? Don't say fantastic set of films from the 2000s onward.
Isn't that just like a group of equations?
A what?
Group of equations.
Is it a group of equations or can they be used in equations?
A box of numbers.
Yeah, box of numbers is probably the best way to think about it. So they both have magnitudes in every location. And they can be considered as having directions, but usually we think of them in the context of vectors as sort of, okay, that we have some three-dimensional space that we're used to. This abstraction here lets us relate either, like you said, series of equations. So you could have a right-hand side, which was z equals something like big A. Let's say that that's a matrix. And then y. So this would be a system of equations that relate on one side all of the vector properties of z to all the vector properties of y. And there are some really important mathematical rules that we'll have to apply here. We're going to go into more detail here. And another thing that I want to show you is that these are all going to be related. And as we move from one to the other, we're going to eventually move towards an abstraction, something that is even harder to physically understand, which would be a four-dimensional matrix, which we call a tensor. Okay, and that in particular is very useful for this type of work. Now you've seen tensors before, and you've seen things like the stress tensor, which was a matrix of different differential gradients in forces or velocities. You saw this in fluid dynamics. So for example, if you have flow that's moving like this, in this direction, but it's changing how much in this direction, there will be a force that's retarding the motion in the direction of the slope, right? Did those words in that order make sense? Okay, just making sure that we're all on the same page here. Okay, so matrices have both magnitude plus two sets of indices, right? Okay. So one thing that we want to check out here is that the world as we know it, the world that we live in, does not care about the mathematics that we use to describe it. So for example, the amount of energy that's in my glass of water or the temperature thereof doesn't necessarily care if it is in terms of Kelvin or if it's in terms of Fahrenheit or terms of Celsius, right? Okay. And similarly, we might say something about the fact that the speed that you're driving should be the same regardless of the coordinate system that you choose. Right? Now, it might be oriented in different directions. So for example, if you're driving on a freeway like this, and you are looking at the velocity vector, and you align it, the direction of motion, you might say all of the velocity is in this direction, whereas if you align it differently, then it would be distributed differently. One of the primary tenets that we need to think about here is that some properties of the physical world do not rely on the coordinate system in which we chose, right? Okay, so we can turn that around. And we can say, what does it imply about the nature of the quantities that are described in this description of processes? So the first question here is, what's a tensor? And I know you all did the reading, so you don't know exactly, right? I've said the word before.
Well, you said 40 matrix.
Okay, yeah, is it only a 40 matrix? No. Are there tensors written on the board already? Good, yeah, one. Anything else?
Well, there's forces.
Forces can be a
I
tensor.
don't think it's true.
Okay, okay, stress tensors. Okay, so that would be which part? Here or here? You said stress tensor. So that's the word tensor, right? So it's associated with the two-dimensional matrix. Are vectors tensors? Scalar tensors. Okay, so the first lesson of today is all of these are tensors. Tensors is the general way in which we describe an n-dimensional data set. That n can be 0. Right? And when I mean dimension here, I mean how many different ranks, and we'll talk about what that means in a few seconds, it has to, how much directionality it has. So for example, a vector could be a 2-dimensional vector, have 2 variables, it could be 4-dimensional, but it's still a vector, goes off in one direction and is described, if you think about it in the context, say, of your computer, as a single row of numbers. A scalar needs no indices to indicate differences, right? It's just a simple value. Okay. So these are all tensors, and we're going to describe them with some notation first, and then we'll talk about how we rank them. Or actually, maybe we'll do that first. So first, we're going to create a form of mathematics that doesn't see the difference between scalars and vectors and matrices. And what we're going to try and do is we're going to connect them seamlessly so that the rules that apply to vectors apply to matrices, and the rules that apply to scalars apply to matrices, etc. So that we can use one single notation to describe them all. So generally speaking, we would say that something has a rank or order. And this describes how many indices do you need to use? So what do I mean by that? Let's start with the first rule. Okay? Spread out of your book, so if you have that and you want to follow along with it, that's perfectly okay. We're gonna start with the first rule, which is the summation. And we are going to not write sums all the time. Okay? No more this. Instead, we're gonna use what's called the double index notation. Oops. Also called because you know with it because it was very much popularized by special relativity and general relativity. Okay. So no more sigmas. So what does this mean? This means that if I write something like a I x I, what is that? And for the moment, we're going to assume for this discussion we're going to assume 3D geometry. So AI xi.
Also be,
So I'm saying now, anytime that you see repeated indices in your mind, I want you to sum over those indices. So that means that if I see a double repeated index at the bottom, this becomes A1 x plus A2 x2 plus A3 x3. Right? That's straightforward.
Yeah.
Okay. So here's another one. I'll write this.
Over the J's.
That's correct. So since the J's are repeated here, I can do what? What's the first one? AI 1. So what we're gonna do here is we're gonna go in order just like we did before. And anytime that you see the repeated index, we're gonna place them. Okay, and so then B 1K. Good. Good. And so the next one,
I
I2. Good. And you get the ID, right? Is that fair? Okay. Similarly, we're gonna say something like this. Something more fun. Add a third object in there. What do you think?
you were.
That's five.
Well, that's a good question, right? So how do sums work? Are they commutative?
Yeah.
I hope so.
I've never seen a double like sigma.
Okay, so let's write it. It's gonna be sigma, sigma. Now, which ones are we summing here? Let's do J, 1 to 3, and K. Right? A, I, J, B, J, K, C. That might be a little obscure, but let's sort of look at it for a few moments. So when I wrote this over here and this over here, the AI and the XI, what was I really writing? Now just look here right now and just imagine what this means to you in normal life, not in weird tensor land.
But it's like a scale kind of.
Why did you assume this was a scalar?
I just wanted to.
But is this a scalar?
You don't know.
How could it be a scalar if there are different components?
Oh, it hasn't been happening.
Right, so here's what we need to do. We need to untrain ourselves that Z means this. And untrain ourselves that A means this. Here in TensorLand, the only thing that matters is how many indices we use to describe it. So how do I know if something's a scalar?
No.
Oh.
No indices. So therefore, we call scalars zeroth rank tensors. Good, and what's the, what are these then?
But that's,
Why are they vectors? They have higher rank, they have one indice each. Okay, so let's look at A for a moment. So let's imagine A is some quantity that has values in x1, x2, and x3, for example. And then x1, x2, and x3 are fine, we understand those sort of well. And that's more similar to these, that they would have magnitude and direction. So you needed only one indice to understand them, so these are first, sorry.
Why are these one, are you saying like the A1 is the one with the first rank?
Yeah, so anytime that something that we're working with,
Is it just because it's only I?
yeah, so we just look at each one of these separately. Right?
I thought it was three-dimensional, so it's third rank, but it's just I, so it's first rank.
Right, yeah, so this is why there's this weird like nomenclature about dimensionality. Maybe I shouldn't have said that earlier. So when we talk about how many, what the rank of a tensor is, we're talking really only about how many indices are required to describe its position. Or sorry, within that space. Yeah. Second what?
Right.
Second rank, yeah, and that is what?
a matrix.
A matrix, very good. So this is the first rank tensor. And here this is second rank. So what does this look like?
That looks like a vector.
Good, that looks like a vector. Does that look like a vector? Good, and what vector is this?
Just to multiply by each other.
What's that called? That is the dot product. Ah, that is a dot product. And what happens in the dot product? What do you get out? A scalar. So in fact, there are properties of tensors which change their rank. Right? So we could go between two first rank tensors, and we can create a single zeroth rank tensor. Right? Okay. So let's look at this one now for a moment. What's this on the left-hand side?
Right here.
Sorry, here. What's that?
Two matrices and a
Two matrices and a tensor.
Wait, doesn't mean a vector.
Sorry.
Oh, yeah, sorry.
Yeah, I heard vector in my head. So two matrices and a vector. So this is second order, first order tensors, right? Good. And what's the product? What do you get when you get out of it? Don't actually try to do the sum. Just tell me what the rank is. It is first. Why is that?
I just,
You just look at what?
some,
Yeah. So if you look at the sum, that's gonna get rid of all the indices, just like we did over here. If you recall, let's take just a normal, this is your matrix A times V. Okay, I'm gonna sort of switch between the various nomenclatures here. And I'll try to only do that really at the beginning, and then we'll be more consistent throughout the rest of the semester. So I take a matrix, say a 2 by 2, and then multiply it by a vector with 2 elements, what do I get out? Let's try this. Is it? How do matrices get multiplied by vectors? Good. So what do you mean by that? Q.
you move it. on top of it.
Okay. Yeah, you can do this in one of 2 ways. I've always done this way to that way. We can do them both ways. Okay, so what's here on the right hand side? Is it a scalar? It's a vector. Okay, so the first element in the vector, this to this is 1 times x plus 0 times y. Right? This multiplied by this becomes the first element.
Oh.
This multiplied by this, 0 times x plus 1 times y. And that, of course, is x plus y,
Oh, no.
x and y separately. What is this matrix right here? This is the identity matrix. It is designed to do nothing to your vector. Okay. So this is I, or the identity. Okay, so it'd be really bad if we hit a vector with the identity matrix and it changed it, right? That would not be identity. So similarly, if I multiply a 0th ranked tensor by one specific 0th ranked tensor, I'll get the original 0th ranked tensor back. What is that specific 0th ranked tensor that I can multiply anything by? Yep. Okay. Here is any random 0th ranked tensor, temperature, whatever, here. Okay. I can multiply it by one very specific 0th ranked tensor. And I'll always get this back.
What?
Correct. Do you see?
Yeah.
That make sense? Is that annoying?
That's a big
No, it's not annoying. This is how you have to think.
question.
No, it's not a stupid question. This is really why language is important. Because if you understand what it means to talk about the identity matrix, it exists as a 0th order, as a 1st order, as a 2nd order, and so on and so forth. Right? The rank of the identity tensor can change, but it's still either 1s and 0s. Right?
This is just the first row.
We're not even done.
Ah.
We're part 3 of 5 of the whole index notation rules. Okay, so let's go back to here. What do you start with?
A, I, 1, B, 1, 1.
Sorry, just like on what rank tensors, let's just go back to the original idea. Yeah.
Oh, that was the.
Second,
Second rank, 1st rank. right? The second rank times the second rank, we don't know what that does yet. We do know that the result is first rank answer. Okay. Does the second rank times the second rank give you a second rank or a first rank?
If they were both JK, it probably would have been zeros, but it has eyes, so it'll be first.
Right, so one thing that we're keeping in mind here is that there is a little piece here. Right, this is the one that's sort of sitting on its own. And this is the only one telling you about the rank of the tensor at the end, because you know that these are gonna be summed over. If they're summed over, then of course they end up at zero. Right? However, one thing we can remember from just matrix multiplication is that if you take two matrices and you multiply them by one another, what do you end up with? You end up with a matrix. So an n by m matrix multiplied, let's write this down because I know I'm losing here. To recap the math really quickly, okay? Here's an m by n matrix multiplied by a n by m matrix gives me
Oh, M by N?
all right, let's look. It's what?
Then by,
Is it?
I don't know what words, but I think it's the same
Okay.
shape.
So let's try it, okay? And we're gonna keep our brains super on top of it today, because I know this type of stuff is, at least for me personally, very stupid. Okay, so let's do 2 by 3. 2, 2, 3. This would be 3, 2. Okay, so I want you to draw out an example. Okay. So you're gonna go 2 by 3. 1, 2, 3, 4, 5, 6. Here. What do you think?
I don't know how to multiply matrices super well. I probably put them in the wrong places, but it's not 1 by 3.
Yeah, 1/3. I just went back here just to make sure that, maybe I should have had a refresher. But, if you're looking in your book, you're looking for, well, I guess if you're using the Hobson Advanced book, you're on page 253. The interesting thing, of course, about the matrix multiplication is that it is not commutative. Right? So the product A times B, both of those are matrices, is not necessarily equal to the product of B times A. Right? Because it'll completely change the shape. So generally speaking, and I like the way that they do it in the book, is that this is what I'm trying to show it to you here. See how they do these boxes? So the first matrix, no matter what it is always your arm flat. And then it slides into the row of the first, right? So let's look at each one of these here. So P, you can imagine this one into this one becomes what?
X1, Y1, plus X, Y1.
Yeah, so this times this plus this times this, right? So let's try and write these ones out. And we'll just call this box here and this box here, right? Going into one another. That's this. Let's call that P11. Okay, next one.
If I got 1/3.
What's that? What's that?
That's why I got the 1/3 of the line.
So this one goes into that one, right? Which element is that?
E1, 2.
Yeah, so that's here. P2. And this one into this one. Okay. Good question. Is there more?
Yeah,
One. And there's eight.
there's two more groups. Second row, the second column, and the third column of the second. Well, you multiple, it's of, the column Y2 and Y5, and then Y3.
Y2.
So this one goes into this one, this one goes into this one, this one goes into this one, right?
Yeah, so you
And that one,
have.
So that's the top.
Yeah,
that one.
So now this row here goes into this row. And then it goes into this row. And then it goes into this row, becoming this row. Right, or no?
Yeah.
Okay, and then what? Right, and so this row here goes into this row. And of course, this became really, really messy, I'm sorry. And becomes,
So that's 3/3.
oh yeah, let's just finish this out. So it becomes P31, P32, and P3. Right? Yes or no?
Yeah.
Happy or unhappy? Okay, and so we'll notice that that is not the same. All right, just erase all this. We'll notice that's not the same as if B multiplies A. Let's just show that one really quickly. right? Where do you end up with there? A 2 by 2. Where all of the elements, for example, you take this one, you put it into here. That's your top element. You take this one, you put it into here, that's your top right element. You take the bottom row, you put it into the first one, that's the bottom left element. And you take the bottom row, you put it into the right, bottom right. So B times A is not equal to A. Right? That's really important to remember there. Okay, I would encourage you, I don't know how good it is in the BOAS section, but if you want, I can, of course, scan this and send it to you if you don't have a PDF of it already. This is all covered in 252, and it shows with these boxes how you can think about it. I've always just used my arms. I'm a physical learner, but you can do the same. Reasonable?
Yeah.
Okay, so sorry for the veering off there. So these two here, we ignore that existed. Right, that's this. Cover that up, you see that up here. Okay. And what is the rank of this thing? Second order, right? So we could already see that this was a second order tensor multiplied by a first order tensor. And therefore, that process is going to end up with, as long as we're summing over those appropriately, a first order tensor. Okay. Okay. Really important rule. We have to be very, very careful with our notation. Okay. So, just as an aside, okay, if you have some vector at some point, you call it ij like this. Okay. And then later on, you have a different vector you call b ij. Okay. And now you multiply A and B, but you don't intend to sum them, you just want to multiply them. What do?
Wait.
Yeah, so you created this. You made this, you wrote this in your homework, then you made this, you wrote this in your homework. And later on, you want to multiply them, but not sum them. When I say it, you're like, oh, that's stupid.
So multiply this, but not sum them. Please don't tell me it's a plus and a cross.
No. It's only about, we're only talking about indices, remember? Today's class is all about letters.
Try that, some.
Oh, the rename the indices.
It's really important that we make a habit of this. Indices are not set in stone. They are not, written down ahead of time, and they're always the same. We need to be very flexible in the way that we think about these letters, in the same way that I talked about it over here, right? So when I said AI, a subscript I, that is your indication that you don't know anything about A other than the fact that it's a vector. And similarly, when you see xi, you also don't know anything about x other than it's a vector. Now, in general, we would use something called basis states, which talk about the orientation of our vectors with respect to real life space. And we tend to use position vectors x1, x2, and x3. Okay? So y and z are no longer a thing to you. Does that make sense? Repeat that back to me. Y and Z are no longer a thing. They don't exist. Right? Because I can do this, right? And I can do this all day long, and none of those are a true X. So it's just a change in basis states. We'll talk about what that means in a few seconds. Fuck, okay, this actually went slower than I thought it would. Thought I was gonna be unprepared. All right, let's do a couple more rules really quickly. What?
The, someone they forgot to choose.
Oh, yeah. Yeah, we haven't even started class yet. I have an hour. No, don't do it. All right. So now we have to talk about our favorite things, which are derivatives. What do derivatives look like in tensor world? Like here's rule 4. What's that? Out of 5, yeah, we're almost done, we're almost done. No, it's not true. Okay. Here's partial VI, partial XI. So what does that mean in words? Correct. Does that mean what we think it means?
Are you saying it's not velocity in space?
Right. Because we don't necessarily know anything about those. I could have used V for viscosity and X for whatever. You should get the idea. Oh, what we know about them is that they're two vectors, right? So how is this written? As a what?
What do you mean?
Just if I were to write out the indices here. So remember how I wrote out the indices for this one? Like that? How did I write these indices out?
You do 1, 2, and 3?
You have to do 1, 2, and 3, right? So what do I do again?
DV1
dv1
over X. Yeah,
correct. Is that it?
well, you gotta
And 2 and 3, yeah. All right. That wasn't so bad, right? But notice what I didn't write. I did not write X, Y, Z. Okay, I'm gonna be really adamant about that. Because when we start writing X, Y, Z, we lose information about whether X is considered a 0th order tensor or a 1st order tensor or something of that nature, right? And more importantly, you can now see the power in here, right? So you see the summation notation is a lot less writing. So once you've gotten used to seeing this with your eyeballs and knowing that it's this, right? I could interpret this thing with my mind physically. I could say this is the sum of the partials of some vector with respect to another basis set. Okay, that's a lot of math words all in a row. But for you, you might be saying something like, okay, well, that looks like a V, that could be a velocity vector, and X could be a position vector. So this could be the rate of change of the velocity in each of the positions. But then it's summed. That's interesting. That's really interesting, huh? Okay, so what rank is the result? 0, correct, because there is no need for an index. So what have I written?
vector, you're deriving the vector, so then that's a state.
Okay, good, that's correct. Let's rewrite this in terms of your vector notation. What is this?
That's a
Can
vector.
you rewrite this in terms of your vector notation, not in terms of tensor notation?
Oh, vector,
A with the line thing.
Good, A with the line thing,
you know, is X.
and X with the line thing? Incorrect.
Dot.
Dot, okay, that's really important, right? Because there's a specific thing we're doing, right? Dot, that is what this is. Right? So what did I do?
Make things look right.
Sure. But that doesn't have a derivative, and it became lower, right?
Yeah. Finding that address.
Well, it's, we don't know exactly, okay, so since it's a vector, that means it can only really change in one direction. Or it's only, what do I want to say? If we were to like look at this in like a vector, it's like, oh, it has like X direction or Y direction or Z direction. So if you were just to derive it, it'd be like, let's say it's only like the vector moving in the X direction. There's only a change in X that's happening, nothing in Y and Z. So it should be zero there, in those two places.
I hear where you're going with this. I'm gonna try and point you to. I wish we just had a. You know, one of those like vector calc. The front of the book, and it has all the different identities.
So,
There is an identity that we're looking at. And I want you to see it with your eyes. Why would it be the divergence? What is the divergence? What does the del operator look like?
it's, oh, it's just the d over d, the vector form d over dx. So d over d, plus whatever you're wanting. I don't know, if it's if it's just the gradient or the del. Isn't it just d over dx plus d over dy plus d over dt? Is that it?
Well, you tell me, is this a vector?
Yeah, you
What?
It's an operator.
It's an operator, but is it a scalar operator or is it a vector operator? It's a vector operator, so therefore the first one needs
Just x hat?
x hat, correct?
Oh, d over dy, y.
And I just told you I would never do this, and then I did it. So that's the gradient operator, right? Okay. So what's this?
Is that just taking the gradient of that?
You don't ask, tell me.
It should just be taking.
This is taking the gradient of that.
Okay.
Does it have, if you take the gradient, if you take, let's be careful about the words here. Is the gradient or the divergence?
That's gradient.
This is the gradient. Okay. So this is taking the gradient of a vector. Is that possible?
That should be, no, it should.
No, you can't. You can only take the gradient of a scalar. You can take a gradient of a scalar field, right?
Hmm.
And we'll talk about that when we talk about, for example, electric potential from the potential field, right? So you go to an electric field from a scalar potential field, right? But what have I actually done here is I have done which process? Del dot.
So that isn't.
Yeah.
Okay.
You see it now? It looks obscure, but it's not. It's just rewriting what you already know. Okay, here's 5, unless anyone has questions. All right, what's this one? Fuck. Not 2.
doing two derivatives, one in terms of x1 and the other one in terms of xj.
No, sorry, these are just both eyes.
Oh,
I
that's
just
both-
drew, I just drew improperly, it's xi and xi.
Oh, okay.
What? Yeah, and so what does that look like? Of x?
So you said they're both eyes?
Yeah, these are both eyes.
Right, just like the partial X. Right.
So,
Like that?
well, x1.
Yeah.
X1, very good. Not x anymore, right? X doesn't exist, neither does y, neither does z. Go with the next one. Same thing, but with two. That's the right way to say it. Okay? Not same thing, but with y. And what's that property? Awesome. So we can convert this into. Right?
Yep.
What's the rank? Make sense?
So that's four, what was the rank of one?
You tell me.
You say first.
What do you think, Rolando?
Sorry,
What's the rank of 4?
so rank of,
Or no, it's zero.
It's 0, right?
yeah, that's two zero. Because, plus that, which is this here.
Does it make sense now? What's Griffith's E and M equation that uses the Laplacian of 5?
Constant phi, shouldn't that, well, that'll zero for sine,
Okay,
for that equals zero for sine.
good.
Um,
0 is definitely a 0th rank scalar, right?
yeah.
That one we know about. Let's use our brains for a second. Let's go back. We know that it has to be a first or a 0th rank tensor. Which of the 0th rank tensors are associated with E and M?
There's charge.
Good. You're done. Right? You don't get to do anything else. Right? So what is the Laplacian of the vector, of the potential, of the scalar potential?
Which is the amount of charge. in the
Yeah.
system.
Right? It's the charge enclosed.
Yeah, charge.
So in particular, what we did is we said, not just charge enclosed. You want to think about it in the context of electrostatics, right? So you have this Laplacian, which is not the J Laplacian, right, which has to do with magnetic fields, which is the vector potential, but this is the scalar potential. And if you recall at the end of ENM2, I claimed that you could construct a 4 vector with 4 elements, where the first element is the scalar potential, and then there is an x, y, z potential for each of the magneto parts, right? Okay, so sometimes we call it J, sometimes we call it H or D, stuff like that. And there's 3 components for these and 1 component for that. So we're headed toward that 4 space, but we're going to continue to stay in 3 dimension. Okay. Just to be clear about something really quickly. These here are called dummy subscripts. They are dummy subscripts because they will be summed over and they will disappear. They do not matter. For example, when I just switched them here, right? Because I wanted to indicate that they are free. These are free indices. Not to be summed over. Okay. Okay, let's do another rule really quickly, sort of a minor rule. All right. What is this? Close. There is a delta. Not quite. So everyone gets to name their own because we're using the same idea here, but it's different notation. So now you get to learn a new fun word called chronica. Chronica delta. So it's pronounced like I did roughly. No one will get mad at you if you don't do it properly. Moniker. Delta. All right, and this is a specific delta tensor. This is a specific delta for tensors that has very useful 1 or 0. So what are the conditions under which it's 1?
Oh, when I moved here.
Good. So when you have a delta Dirac function, right, that's something like this. What do you have there?
You have 0.
At all
You would have 1, you would have 1. It would equal 1.
at what?
X equals A.
At x equals a, right? So this is the delta Dirac function. You'll notice it's very similar here to the Kronecker delta, except that we're going to use it in the context of matrix manipulation, vector manipulation, tensor manipulation. Okay. So let's see a really quick example of it.
Oh, so it's,
So wherever I equals J, then just get B.
B subscript.
Or B2.
Okay, first let's talk about the rank.
Well, it's the first rank,
It's the first rank. What?
because it's just, it is B subscript J.
Good. So B subscript J is itself
Okay.
a vector. Then I multiply it by the Kronecker delta, which is itself a
Scalar.
incorrect. Right? Which rank is it? 2, because it's IJ. Right? Okay. So I have IJ here. And how many free indices do I have? 1. And I have 2 dummy indices. So that means that exactly like what Rolando said is that we will end up with the first order tensor. But what will it look like?
P1, SI1, and like 2s, but will it be 0 with wherever the I is not the number?
Right, so it has to be 0 wherever I is not the number. So how would I write this right hand side? Well, it's quite straightforward. Like that. I know that feels silly. It feels silly, but we're just learning to walk again, right? Okay, it wasn't obvious, but we have to remember how we use the Kronecker delta in these situations. So this is essentially going to let us change coordinates if we need, change indices if we need to. At least you read?
No, I think I just should.
Okay, it's done, but it's helpful. Okay, so let me ask you this one. You ready for another one? No, fucking tail, was so good. Alright, that, good. So also. What? You see how those are the same thing? What?
Is that equal each other?
Well, just because I get, what I'm trying to say here is I can switch these, no problem.
Because they have to equal each other?
Yeah, sure, exactly like you said. And so similarly, the whole equality has to be maintained, so this is of course equal to this, and this is of course equal to this, like Rolando said at the beginning, right?
Couldn't it also just be AIG then?
AIJ? No, because I have a W in this, because I'm seeing over.
Oh, you summed over.
I summed over the J's, so the J's are gone. Anytime I see a repeated index, that is gone in my mind. Right? Okay, even if I don't do the sum. Okay. What about this one, last one, and then we can move on. What?
G, I was reading G or J. J,
This is a J.
Yeah.
Yeah, these are J's, yeah. What do you got here?
S, C, A, J, J. I don't know.
Okay, so what does the chronic delta do here?
If K equals I, it's one.
Right. So essentially what it's gonna do is gonna replace all K's with I's or all I's with K's.
It's gonna replace.
It's gonna replace all K's with I's or I's with K's. That's the
But
property.
you're
of the chronic.
summing over both of them?
Yeah, and I'll write the double summed version in a second, but I just wanna write it in terms of using this property of it. It's basically a replacement method, right? So whatever these variables are, sorry, whatever these indices are, you're just replacing one with the other.
But they're also disappearing.
This, yeah, this will disappear. And then later on, we'll-
The I's.
correct, right, because there are double pairs of them, but I could have written it different. Right, I could have written that these were not repeating. So I could go here, IJ. B. J and I. Right? That would be,
I's are gone.
well, they will be gone when we do the sum. Right, the K's would disappear here, but this is also equivalent to just saying. In this particular context, I could say it in one of two ways, it wouldn't be equal like this, because obviously they would have different letters. But this one would be, if I replaced the K's with I's, then I would go.
You can't have repeating indices, right? You can't have JJ, that would be wrong.
Here, JJ,
On the right, like if you wrote the same letter twice, that'd be wrong.
not necessarily, you just can't write it 3 times.
Why?
That's the rule, so the rule is you can't write it 3 times.
So you could be AJJ, you could be AJJJ.
Well, you can't have, okay, so, so you can't have. This. Alright, hold on, that's not a good example, that's the chronic delta. Hold on. You can't have. You see why?
No.
Okay, basically what's happening here is there is, the way that the tensor mathematics actually ends up working out is that that's just not how the indices sum. So when I go through that process of multiplying like this, multiplying like this, multiplying like this, I can't get a sum along 3 indices at the same time. I can only get it along pairs of indices, based on the fact that each matrix only interacts with its nearest neighbor and can't go over to the near neighbor afterwards. I could do them in succession, there's nothing wrong with that. Right, I could do the sum on J, and then when there's a new variable, I can use that new variable again. But generally speaking, what I need to do is I need to do this and turn this into a different letter.
With the marker?
No, just with my hand.
Okay.
So we need to be really careful when we do these sums and we're working in Einstein notation, that we're not repeating indices all over the place unless we intend to do the sums. Make sense? This is talked about a little bit on 928, if you're interested. Okay. All right, how's that feel?
I forget which textbook is that?
This is Riley Hobson and Benz mathematical methods.
Okay.
Okay, I really thought that I had not prepared enough, and instead I think I prepared too much. So we're not gonna talk about change of basis today, unless folks are really interested in that. But what we'll do next time is we'll talk a little bit about change of basis and Cartesian tensors, specifically the transformation tensor, and how quantities are conserved through use of specific tensors. So we've seen a couple different tensors to conserve quantities before. Does anyone have an idea of that?
Wait,
The what?
that's-
Something to conserve, you said?
Yeah, something is conserved even after. Well, let me finish the sentence and then I think you'll probably get it.
Okay.
If you have a quantity that is conserved even after applying a specific tensor to it, to change all of the elements in the original matrix.
Identity?
Sure, that's a great one, right? That's the easiest one. And is there any others?
Actual, like, real world example for this.
Yep, that's what I want you to do. I want you to think about the physics. I know we just talked a shit ton about math.
Something where you multiply by it and it doesn't change anything in physics?
Well, so like something constant.
Something that might be conserved under certain types of things that happen to it.
I was gonna say fluids, like the amount of.
What about say, if something is invariant under rotation? So even though you change your coordinate system, maybe the velocity magnitude stays the same. And that would be an example of applying a rotation tensor to the vector and still ending up with a physically meaningful object that is the same as what you started with. So we'll talk about that in the context of 3D Cartesian geometry. And then we'll very quickly basically just go off into the netherworld. And we'll talk about 4D shit hopefully next Monday. Maybe that's too bold, but we'll see.